start finding the magnetic field going in versus out?
As it started there? Or the fact that if that's going up, this is coming out?
Right, that,
If that's going up, this is coming out?
it can't be going in.
No.
Okay.
Because it turns out, and I'm skipping over the reasoning behind it, but the direction of, so if I did, let's say, direction of the electromagnetic wave, so remember that the direction of velocity is the direction of movement. That's the direction of E cross B. So E cross B tells you the direction that the wave is moving.
Okay.
So the wave's moving this way.
Right. Okay, thank you.
So now we have 2 dimensions.
Well, at any particular moment, so at one particular moment we have yeah.
I mean, I guess if you looked at it from the other side, like from a different plane, it would look like 2 dimensions at one time.
As in, you're standing over here?
Right.
Yep, pretty much.
So-
Now, in reality, I simplified it down to just this one electric wave field, this electric field and this magnetic field. When we talk about, think about the light coming from above. The electric field's in all sorts of directions, and there's a magnetic field perpendicular to it in all sorts of directions as well. I mean, it's coming at us unpolarized. What Polaroid filters do, Polaroid sunglasses do, is that they eliminate parts of the electric field that are perpendicular to the way you have the polarization set.
Dr. Fox,
Yep.
could you explain, I'm sorry if you already did this, but explain the formula that you wrote in blue underneath our,
This,
yeah, is that speed?
that's the direction of the velocity
Okay,
of the electromagnetic wave is the same direction as E cross B.
okay, and since they're perpendicular, they will, okay,
All I care about the direction piece of it, so the electric field's going up, the way I've drawn it, electric field's up, magnetic field is this way, so E cross B would be like that,
that's the direction of the velocity,
and the thumb points in the direction of the velocity.
okay.
I'm not sure I made that better, but I was at least trying to have some sort of color coordination there. And then, all right, so if I have an electric field that's described like this, and the magnetic field and the electric field, they peak together, they are zero together, they trough together. And so the magnetic field's gonna have the same wave number and the same angular frequency, same speed. So the magnetic field is gonna look a whole lot like that, except the maximum value is the maximum magnetic field times the cosine of kx minus omega t. And so now, let's apply Ampere Maxwell's equation first, and then we're gonna apply Faraday-Lentz's law, and magical things will happen. So what I'm gonna do is I'm going to take a small little section right here of my electric field. I probably should have done that in a different color just so it contrasts. I'm gonna take the small little section, I'm drawing it really big here, but we imagine that my axis right here, I'm just taking a small little bit. My electric field is going up at this moment. My magnetic field is coming out. I'll represent the magnetic field coming out by, I've got these dots here. Coming out. I'm gonna draw this bigger. Because again, my electric field is up, my magnetic field is this way. So if I looked at my electric field, so the electric field's doing something like that. I'm on the upswing right there, just the way the point I picked. My electric field at this point right here. So imagine I got this point in space, my electric field is just some value I'm gonna label as E. My electric field, just a little bit after that, is E plus some change. There's some difference between it, that's just putting delta E there. I'm going to apply Ampere's law. It says that if I do the sum of the electric field dot delta L around some loop, I'm going to end up with, well, I have no traditional current here, so this just can be reduced to U sub naught, epsilon sub naught, times the change in the magnetic flux, or the change in time. Do you want B or M? Do you care?
I do not care.
Okay.
Is it representing magnetic field?
Yes.
Then I would rather it be B, since we.
Okay. The subscript, this is for magnetic flux here. So this is the electric field that is created from the change in the magnetic flux. And that's what I want. Yes, it is. Yep.
You said this is the magnetic field created as a result of the change of the magnetic.
This is the electric field that's created as a result of the change in the magnetic flux.
Okay.
All right, so what I'm gonna do is I'm gonna do this dot product between my electric field, my vector symbol's gotten really horrible there, between my electric field and the length. Just the electric field times the dot product with the length. Because this red square right here is a physically, I just got this rectangle in space. I'm gonna make the width here some small change in x. If this were calculus space, I'd write dx. My height, h. It's gonna go away. It's just some letter, a throwaway letter. But I need some height there. And the ray, I'm gonna work my way around, because this is, I'm basically going around in a line, getting back to where I started. The circle means I have to end up back where I started. Right hand rule, I'm gonna go around counterclockwise, because if I go around counterclockwise, magnetic field's pointing out, same direction as my thumb. Just go with it. I'm gonna start here. This first branch right here, I'm just gonna label A, then little b, then C, and then little d. So I have my electric field dot, we'll call it delta L sub A, going along there, now I'm going up, plus, call that E sub A. My electric field along B, dot delta LB, plus my electric field C, dot delta LC, plus my electric field along D, that last path, dot delta LD, is equal to U sub naught, epsilon sub naught, times change of, what is magnetic flux anyway?
Isn't it like a cosine equation? It's like,
Yeah, cosine can pop into it if it's not how you want to write it.
Would it be B dot A?
Yes. Or VA cosine theta, if
Right.
you want to throw the cosine in, but B dot A is the one I want. So I've got this surface right there, I've got this rectangle. What's the direction of my area vector?
4?
Okay. Yeah, it's perpendicular to the surface, so we're gonna pick the same direction as D. All right, so along here, along this path, as I'm moving to the right, what is E dot that length? Feel like we've been away for a month.
Well, they're perpendicular,
Yeah, so.
Therefore,
it should be 0.
yep, 0.
Sorry.
No, it's okay.
Along the next path, I'm now moving up. What would this be?
L is just like the length, right? What is L?
The length of my rectangle.
So, E. And then B. They're in the same direction, right?
Yep.
So it's like the maximum? Is it just 8? Wait. Is it H or B?
8, so this would be H. And this,
E plus delta E.
yeah, so this is E plus delta E times H. Thus, we're now on the C section.
Delta X?
0 again?
Could be
wait.
0 again.
Oh, sorry, I didn't see the dot.
E is still going up.
Right.
And then the last bit, so I've gotten to here, I'm now moving back down to where I started.
Is it going to be E times whatever that length is gonna be?
H.
Is it still H?
Yeah, H is, it's a rectangle. So the distance up is the same as the distance down.
Oh, I'm sorry, I just was thinking like it stopped where the electric.
No,
stopped, like it
physically
was-
going back to the starting point. There's one small issue here.
What happened to the delta E? If we still have to cover that full distance, I'm confused about why it gets dropped. Oh, right.
The electric field is not the same here.
Distance.
So this is just the difference between the two, like the electric field at this point and the electric field at this point.
Right, H is the distance. Okay, I think I got it.
Is the problem with it, we haven't set it equal to like u sub naught epsilon?
No, not, we can do that, there's a problem with this term right here.
Oh, it should be negative.
Yes. Because I'm traveling down, but my electric field is up, they're in opposite directions, so negative. Over on my right-hand side, my area of my rectangle there is not changing at all, so that can just move right out. B and A are in the same direction, so this can just reduce down to mu sub naught, epsilon sub naught, A times delta B over delta T.
Where does the A come from?
The magnetic flux is B dot A. And so B and A are in the same direction. So the dot product is just the product of B times A.
Right.
A doesn't change, so it pulls out. This is the area of the rectangle, it's H times delta X. All right, here we go. I'm gonna distribute over here. So I have E, H plus H delta E minus E H equals mu naught epsilon sub naught area, which is H times delta X, times the change in B over the change in T, which I'm just gonna leave as that. We now get rid of stuff. Welcome back. I'll see you tomorrow. All right, what do we get rid of?
EH? I think it's allowed.
You said EH,
Yeah, what you cross out.
and what can we get rid of now?
0 H.
Yep. And so what I'm left with, and this delta x here, I'm gonna take on over to the other side just because I know where I'm heading on this one. So I end up with delta E over delta x equals u naught epsilon sub naught delta B over delta T. And I know what you're thinking. You're going, wow, that's just incredible. But can we do more with that?
I'm actually so.
Oh, sure we can. Oh, yeah, we can. Because I have two equations right there, and this is just the slope of my electric field times versus position, and this is just the slope of my magnetic field versus time. So let's do it. The slope of this right here with respect to position. Well, first off, cosine becomes what? When I'm doing slopes.
Negative sign.
Yep, all right, so I got a negative sign there. And I'm still gonna have the kx minus omega t there. What's going in front?
Give me a second. Is it going to be that slope multiplied by kx minus omega t?
Or kx minus omega.
Just that we're doing this with a change with respect to position, so when we're doing that, we don't care about the time piece, so it's just the k.
Okay, so delta E over delta x times t. 'Cause that's the slope, right?
Now, just like we had done over here, which now erased, we do the change in some cosine, and then we take whatever we have in front, that stays there, and then we multiply by whatever the coefficient is of the denominator, so it's just gonna be k times e sub n.
What's E sub n in this problem?
What is e sub n?
Yeah.
It's
Didn't-
whatever the maximum value of the electric field is.
Oh, so we don't know it yet.
No, we don't need to know it.
Okay.
And on the right-hand side, the first one was rough, the next one will get better. This is mu sub naught, epsilon sub naught. Change in B with respect to time.
Okay. So T times B of n? Wait,
Not T,
omega?
close,
Negative omega?
yes.
Okay, negative omega, times B sub n.
And then,
Negative sign, right? Wait, no. Does it go from negative sign to negative cosine for this one?
it goes from,
Cause it's cosine,
it's cosine,
so it should be negative sign.
yeah.
So the negatives will cancel out there.
We got messed up with a minus sign somewhere. Minus sign that would have lost. Around that way, that's all good. That's right, that's right, those go away. That's all good. This sign becomes negative sign. Where did my negative go? So then you would have negative sine of kx minus omega t. All right, let's figure out what I did with the minus sign. Magnetic field's coming out, so that's A delta D, change in D or change in time. Usually I start out with sine, but that should not matter. Oh. No.
We believe in you.
The brink of genius.
Boneheaded mistake. This is not Ampere's law, like I said earlier. This is Faraday's. You got the L. Negative. There's a that's what the extra negative is.